Good morning, everyone, and welcome to this Chromatic Dispersion WebEx session. My name is Xavier Rivard. I am a training coordinator at Expo. I will be the host of this session today. So basically, I'll explain a little bit how this session will be conducted. And I will also present my colleague over here, Gabriel Kerwin, which will be the presenter of the session today. Basically, the WebEx will be in a 1 hour session. The topic of the day is the chromatic dispersion. We will also allow some people at the end of the session to forward and express themselves throughout the question in the chat Q&A that you can find at the lower right corner of your screen. Every single question will be responded at the very end of the session. So throughout the session, if you do have any question, please write it down into that Q&A section. And basically, once this presentation will be over, we will go after each single questions, and we will try to do our best to respond to those ones. For people that are inquiring for some audio sound, unfortunately, it will be only a one-way speaking session. So basically, we are the speaker, and you guys will be passively attending this session. I will quickly pass on the microphone to Gabriel Kerwin, which will present himself today for this session.
Thanks a lot, Xavier. Welcome everybody to this presentation on chromatic dispersion. My name is Gabriel Kerwin. I'm a technical training specialist here at Expo. What we are going to be doing is having a presentation, first of all, on a chromatic dispersion. So we'll sort of review what is exactly, what are the causes, as well as a little bit of information about how chromatic dispersion can accumulate from a fiber link. After that short presentation, we're going to jump over to the equipment side of things. We have a dual-ended test set, which is running on an FTB 500 platform. We have an FB5800 chromatic dispersion module, a broadband light source, which is the FLS 5800. Then after that, we'll look at the single-ended testing equipment, which will be an FTB 5700 module running on a FTB 200 platform. So we're going to go through the presentation and then the review of the equipment menus. Like my colleague mentioned, at the very end of the session, once we're done presenting all of this stuff, we will get to the Q&A portion. So anyone who has any questions, they can stick around, and we will be answering each and every question at the end of the session. If we get started here with our presentation on chromatic dispersion, chromatic dispersion is the spreading of an optical pulse as it travels through a fiber link. The spreading is due to the different wavelengths which are composed within that pulse. Will be traveling at different speeds. So like we can see here in this presentation, your initial pulse, which is on the left, is very, I guess you could say, short. And as we get further along the fiber, which would be towards the right, the pulse spreads out and also loses a bit of its intensity. We can see that the top of the pulse, or the peak of the pulse, actually goes down. So it loses a bit of power. What we're looking at here is a graph showing us, first of all, along the x-axis, we're looking at different wavelengths, and along the y-axis, we're looking at the dispersion, which corresponds to all of these different wavelengths. What we can see is the upper curve is a dotted line with the word material, this is a contribution of the fiber itself. The composition of the fiber is contributing to the dispersion. And beneath that, at the bottom of the graph, we have a second dotted line which corresponds to the waveguide dispersion. The waveguide dispersion is due to the nature or the shape of the fiber itself. If we combine the two, we get the total dispersion, with that solid curve right in the middle. We're going to look at this actually in a little bit more detail now, each of these. Okay, material dispersion, one way of looking at it is to use two wavelengths which are very close together. However, they do have a small difference in wavelength, so in this case 1458 nanometers and 1550 nanometers have a different wavelength, or we could say spacing between the peaks and the valleys in each one of these light waves. As a result, the speed at which these wavelengths will travel through the fiber will be different. So that's what we can see here down at the bottom. Both of these wavelengths will be traveling at a different speed through the core of fiber. Coming to cause number two, we're talking about the actual waveguide dispersion, how that contributes to the chromatic dispersion. So what we have here in the top of this graphic is the profile of refractive index of a typical conventional single-mode fiber. So what does that mean? Well, that means that in the center of the fiber, where we have the core, we have one type of index of refraction, and as we get further out from the center of the core, we eventually reach the cladding, which has a different index of refraction. So that's what that value n stands for in the graph. N is the index of refraction. In a different type of fiber, which would correspond to the second part of this graphic, we would have a dispersion-shifted fiber. Now, the dispersion-shifted fiber has a different refractive index profile, different than single-mode standard telecom fiber. There's actually a central area or a core area where we have a graded index. That's a diagonal line close to the center. And further out from this core graded index of refraction, we have two lower levels, or two other levels of step index values. Now, what this is going to do is it's going to create conditions that change the way that chromatic dispersion occurs as the signal travels from point A to point B in the fiber, and it's going to dramatically decrease the amount of total chromatic dispersion that occurs in transmission. So see what this looks like when we put all of these different types of fibers together in a graph. Before we get to that graph, I'm just going to have a quick look here at how different wavelengths have different amounts of the energy or pulse traveling through either the core or the cladding. What we can see from this graph over here is that the larger wavelengths, in this case lambda number 3, the more the energy is traveling through cladding and only in the core. So versus a shorter wavelength like lambda number 1, a lot more of the energy is traveling in the core and not in the cladding. So we can sort of get an idea as how you use a dispersion-shifted fiber. You're actually going to be modifying the composition of the cladding and the refractive index of the cladding to decrease the total amount of chromatic dispersion that occurs. So what we have here is a graph of the different types of fiber. The top curve, which is actually very pale here, it says dispersion unshifted. That's G.652. That's your typical standard telecom fiber that's going to be found in many places. And if we look at the value in the x-axis of 1550 nanometers, that's where we have that vertical dotted line. Well, if we intersect 1550 nanometers with the curve of the G652, we get a value that's roughly at 17 picoseconds per nanometers kilometer. So for standard telecom fiber, this is how much, approximately how much chromatic dispersion is going to be accumulating for each kilometer of fiber. So if I have 10 kilometers of this fiber, I will accumulate roughly 170 picoseconds per nanometer of total dispersion. Now, beneath this G.652 curve, with three other curves, we've got dispersion shifted fiber and two non-zero dispersion shifted fiber. So we've got the G.653 and G.655. These are the fibers that contain the different refractive index profiles, and as a result, we can see how that affects the overall chromatic dispersion being accumulated on these fibers. So they're very, very close to the zero value. The G.653 is actually roughly at 0 picoseconds per nanometer kilometer. And non-zero dispersion shifted fibers, the G.655s, they'll be a little bit above or a little bit below the zero value. The reason that these will be a little bit above or a little bit below is that when you have a zero chromatic dispersion fiber, 0 picoseconds per nanometer, we open the door to other types of issues that can arise, such as four-wavelength multiplexing and things like that. So we might find non-zero dispersion shifted fibers instead along our networks. We'll see a little bit more about that as we continue in this presentation. So we're talking about how CD can affect your transmission. Depending on the data rate that you're going to be using, there will be certain tolerances acceptable or accepted by the receiver at the end of your fiber length. So based on the transmission speed that you're going to be using, you will have different tolerances. And for example, we can look here at 2.5 gigabits per second. We get about 16,000 picoseconds per nanometer of total tolerance. So that's actually quite a lot of tolerance. We can have a lot of chromatic dispersion without having it affect our 2.5 gig signal. As we move on to 10 gig and 40 gigabits per second, the values of tolerance decrease dramatically. For 10 gigabits per second, we're roughly at 1,000 picoseconds per nanometer. At 40 gigabits per second, we're roughly at 60. Now, these are for typical receiver systems. Know that there are also coherent receiver systems out there. I don't know a tremendous amount about these coherent systems, but I do know that their tolerance levels are higher due to the multiplexing and the way that the signals are sent through fiber. The coherent systems have higher tolerance levels. Here's a visual representation of how the dispersion can affect your signal. We can see in the upper left-hand corner, the first signal is not showing much dispersion versus the lower right-hand corner. We can see how dispersion can take over and effectively confuse the receiver on the far end, and it might be unable to distinguish between bits and data rate. So there are two different types of testing for chromatic dispersion on fiber. The first type is the dual-ended test set. Dual-ended test set uses a broadband light source and a chromatic dispersion analyzer in between or on either side of the fiber length that's under test. And this is actually the setup that one of the setups that we have here today. The second setup use a single-ended test measurement equipment. So we will be using the, in this case, an FTB200 with the 5700 module. And the reason that I put OTDR in the presentation is that this type of module, the single-ended test measurement, going to be using OTDR technology to measure back reflections at all different positions along the fiber under test, and use combinations of OTDR wavelengths to be able to calculate the dispersion or the differences in arrival times between these different pairs of lengths. I also have this set up ready here to go. We will be looking at both types of equipment and both types of menus, and we'll be getting to that very, very shortly. Now, if we take a quick look at how this representation is showing how chromatic dispersion increases or accumulates with distance, I should say. Different wavelengths will have different amounts of chromatic dispersion accumulating along the way. So we can see that in this visual representation, the different colors will represent a different wavelength, and after a certain position, we'll each have different amounts of chromatic dispersion accumulated along the way. Now, the idea is that over longer distances, we would maybe consider using compensators, dispersion compensating fiber, to effectively bring dispersion levels back to, I guess you could say, a level at which the seed can begin to accumulate again and essentially start a pattern that can be repeated over a long distance. So by the time you get to the end of your link, you will have a low amount of total chromatic dispersion. So there are ways to compensate for it as you go along your fiber link. The trick in this is to determine where is the best area to use these dispersion compensating fibers. So looking at standard telecom fiber, which is accumulating roughly 17 picoseconds per nanometer of chromatic dispersion along the way, we're looking at an area of roughly around the 60 to 80 kilometer range is where we would want to target using one of these dispersion compensating elements to bring back your chromatic dispersion to a level from which you can continue sending your signal through the fiber, and that by the time it gets to the end location, there's still a relatively low amount of dispersion to tolerate your transmission speeds. Another alternative would be to, instead of using standard single mode fiber, you can use alternating lengths of the non-zero dispersion shifted fiber. If we, for example, use alternating sections of, let's say, 20 kilometers or even 40 kilometers or more of the positive non-zero dispersion shifted fiber, and then followed by the negative non-zero dispersion shifted fiber, we can see how over distance the total compensation, the total chromatic dispersion will stay within manageable levels for receiver receipt of data. So that takes us through the presentation part of chromatic dispersion. Simply put, it's an accumulation of dispersion over different lengths of fiber, and it is due to the differences in speeds at which the different wavelengths travel through the fiber. So what we're going to do is we're going to start by looking at a dual-ended test measurement with the FTB 500. So from here, we're looking at the FTB 500. We see the main menu at which we see our perimeter screen. One of the first things to do, now this is a step that I did before beginning the presentation, just to save a little bit on time, is to, down here we have the Take Reference button. This is going to be in the lower part of the screen. If you hit the Take Reference button, reference menu or reference window here showing us two tabs, C and wavelength. Now, wavelength reference is important to before we take our measurements on the fiber under test. The reason being that if we do not do this reference, the information that comes into the CD analyzer will not be accurate and will not give us the appropriate value of chromatic dispersion. So all we need to do is get to this part of the menu and click on the Take Reference button, which like I said before, I had done just before starting this session. Now there's another tab over here for CD reference. It's basically another type of reference to reference out your type of light source, in this case the FLS 5800 broadband light source. If using different types of or different light sources, such as an FLS 110, or maybe you might have several different light sources of the same model, this is a way to instruct the CD module which one is being used. That's why there's a place for entering a serial number here, as well as the source model. So different ones can be used. Now, in case where I'm going to take the reference here, we have a message in the lower bottom portion of our screen telling us that it is recommended to perform a wavelength reference. So I'll do that right away. It should about 30 seconds or less. Now, while wavelength reference is being done, we're going to head over to the parameters screen after this, so we can look at what are the different acquisition parameters, such as range, step, and averaging time. Almost. Okay, so the unit is ready to go. Now we look at our parameters. First parameter, your range. You can choose to test in the C band, the L band, or both. You can even customize which wavelength range you'd like to test at. If you like, you just set dial to the custom button, and then down here you have your range beginning and end for the customized setting. Next parameter is the step setting. You choose to take a measurement at every 0.2 nanometers, 0.51, 2.5, and so on and so forth. You can even enter in a customized value. All we need to know about this parameter is the shorter the step, the more data points will be acquired, and the more data points will be acquired, the more precise your CD measurement will be. So I guess the shorter the length, precision is a lot less affected by choosing a longer step. So for example, if I'm testing a short fiber of 20 kilometers or so, which is the case, I think I can get away with testing at 1, 2, or 5 nanometers, simply because it's a very short fiber length, and so there will not be a lot of chromatic dispersion that accumulates over this short fiber length, and therefore the precision will not be greatly affected. If I'm testing, let's take an extreme example, a 400 kilometer link, and I want to get a very accurate result of chromatic dispersion for this 400 kilometer link, then I tend to choose the 0.2 nanometers or 0.5 nanometers step. As a result, get a more precise measurement for the longer fiber length that would be your test. Finally, we have the averaging time. This is the amount of time at which each step will be measured. So 1 second, 2 seconds, 5 seconds, so on and so forth. Generally, I'll recommend using 1 or 2 seconds for shorter links and 5 or 7 seconds for longer links. One way of being able to tell if we chose a long enough time or not is we'll see when the data acquisition is done, all of the points, they either be in a relatively smooth curve. If they are in a relatively smooth curve, then that means that my averaging time was just fine. If I see in my data points points that are sort of straying from the curve that might look a little bit erratic, that is the indication that my averaging time needs to be a little bit longer. So now that I've chosen my testing parameters, down here in the lower left-hand corner, I can choose the different type of a fiber that I'm going to be testing with. Now in my case, I know that I have standard fiber. There are the other types of fiber there as well. Even if we don't know what is our fiber, we can choose unknown fiber type. As a result of choosing the fiber type, there will be a data fit, a corresponding data fit that will be chosen automatically by the equipment. Now we can change it if we like to any type of data fit, but based on the fiber type that we choose, it will choose the correct associated data fit. What the data fit is going to do is take the total amount of data points acquired and extrapolate a chromatic dispersion curve for all different other kinds of wavelengths. Now, if we know our fiber length, this is where we can enter it in this checkbox right here. This is the actual fiber that I'll be measuring today, a 17.24 kilometer fiber. If at any point we do not know our fiber type, that's okay. We can uncheck the box and still do our test. At a later time, once we have measured the length of our fiber, we can always come back to our results and enter in the known fiber length to get our associated chromatic dispersion value. Now, once the parameters have been set and the fiber information is ready to go, we simply hit the Start button, and we will see data points slowly starting to get acquired. So you can see the points starting to accumulate. This is for each step measuring the relative group delay value in picoseconds. It's going to continue we reach the end of our range that we wanted to test at. There will be certain points that appear in purple. They are our data points. Other points will appear in gray, such as the case right now. We see a few data points appearing in gray. What the gray data points are is the reference wavelengths at which the CD module is testing at. The reason that I use the word reference is that in order to calculate the relative group delay values of all the different wavelengths, the chromatic dispersion module uses a few specific wavelengths as the reference wavelengths with which to compare the other steps at which we get measurement data points. Okay, we're almost done with the acquisition. Okay, so our acquisition is done. We have our data points here in the graph, and we can see information right here in the middle of our menu. So at the 1550 wavelength, which is highlighted right here, we see a dispersion value of approximately 16.957 picoseconds nanometer kilometer. So this is the amount of chromatic dispersion that we roughly expect to see for a standard telecom fiber, around 17 picoseconds or so. If we want to, we can move our wavelength marker around to go look at the value of dispersion for different wavelengths, if that interests us as well. Beneath the results graph, over here, we have a magnifying glass which allows us to zoom into different portions of our graph. For example, let's say we wanted to use the data fit and see where our dispersion value is close to a 0 or a different value. All right. Now you can see how the data fit has extrapolated the data points, which are the purple points over here on the right-hand side of the graph, and extrapolated what kind of chromatic dispersion values we can expect to get for 1500s or in the 1400s and so on and so forth. So if we're using this test equipment to simply qualify a fiber and see what's the total amount of chromatic dispersion that occurs, all we need to do is set our parameters and then look at the dispersion value over here for specific values. Most likely it's going to be around 1550 if we're looking at a base value of chromatic dispersion. From there, we can do other things, such as in the parameter screen. If we like to, we can choose to take multiple acquisitions. We can select how many total acquisitions will be done, as well as what is the time between acquisitions. This is if we want to measure, let's say, an evolution in chromatic dispersion over a 1-hour period or a 24-hour period, depending on what we'd like to be testing for. So that's an additional functionality of the tester. Our results graph tab is over here. Our results table will show us the individual points, what kind of results or data did we get for each of the different acquisition points that was done during the acquisition. And the final tab over here of acquisitions will basically show us if we're working with one fiber or multiple fibers, what is the measurement that we can see. For example, if I load another fiber here, which is a different file which was taken at a previous time, we can see that this fiber is an 80-kilometer fiber, and there are 8 acquisitions were done for these fibers. We can look at them on the results graph, and we can see different values for this different fiber. So in the case of this particular fiber, let me bring it over to 1550. There we go. We're getting a roughly 16.7 picoseconds per nanometer a kilometer. Now, if we quickly look at some of the other options on the FTB 500 with the FTB 5800 module, there is the setup button over here. In the setup button is where we can come and change if we want to use miles or kilometers. There are options over here for the graphic display. For example, if we want to show the fit lambda 0 value, that will appear on your graph. And down here is where we can get thresholds applied. If we have a limit threshold for either the dispersion coefficient or the total dispersion being measured over a fiber, this is where we can come and enter in the values. So, for example, for OC48 or OC192, there would be different threshold values that can be applied. We can manually enter them here in the setup screen. What we're going to do now is we're going to move over to the other piece of equipment, which is the FTB 200 with the single-ended dispersion analyzer. And what we're going to see there is that the threshold values are already entered into the I could say the parameters screen for your test. So I can choose them there. Okay, so let's bring up. So everybody can see now the FTB 200. This is the main menu as we start our module. We'll go to our single-ended test analyzer module and load that application. So it takes a few seconds for the module to initialize. And it's ready to go. So the single-ended test measurement module has a lot less parameters to enter in. The equipment is very user-friendly. Actually, the only things that we need to do is choose whether or not we're going to use the CD measurement and the PMD measurement. We can do both for one or the other. For today's demonstration, we're going to be using only the CD measurement, and in our next presentation, we will use the PMD presentation. The other parameter to enter in is if we want to change the name of the fiber prefix and the fiber number, and if we want to apply a threshold right away for test. So we can choose the threshold of none, or OC48, OC192, OC768, and so on and so forth. So let's do a test for an OC48 measurement, and we simply need to hit the start button. So the first thing it's going to do is evaluate the length of the fiber being tested. Right, so it's evaluated the length at being in roughly 17.24 kilometers, just like we had in the previous equipment. And the CD acquisition is roughly a 20-second measurement, so it's a little bit quicker than the dual-ended test set. Okay, so we have our results right here for the CD measurement. We can see that the total dispersion being measured in is 293 picoseconds per nanometer. The coefficient is roughly 17 picoseconds per nanometer, so that's what we would expect to see. If we compare values to what can be tolerated by a OC48 receiver, we're within the range of 16,000 picoseconds per nanometer. We can apply different thresholds to this result by changing our parameters down here. So in this case, at OC192, we still have a pass, and at OC768, well, now we have a fail. The tolerated value for OC768, which is a 40 gigabit signal, was roughly 60 to 70 picoseconds per nanometer. In this case, we're over 293, so that's more chromatic dispersion that can be tolerated by that type of transmission. We can look at more details about the actual fiber acquisition here in the CD details button. So we have our graph showing very similar to what we saw in the previous type of equipment, the dual-ended test set. We've got our wavelengths on the x-axis and the chromatic dispersion in the vertical axis. The different data points that were acquired appear here in the lower right-hand corner, so we can look at the data that's there as well. And the summary appears over here in the lower left-hand corner of the main menu. We can see information about that, about what was used during the acquisition. From here, another functionality that we can look at is in the setup. We may have, again, like before, measurement units can be chosen. We can choose to keep intermediate data in the case of multiple acquisitions. This is a good thing to do if we want to analyze the results after an acquisition, sometimes only the summary will appear. If we check this box that says keep intermediate data, then the file will contain all of the chromatic dispersion results. If there were multiple results done, it can be done there as well. In the acquisition tab, we can choose to change the default range which we do our testing. The fiber type can be chosen here as well. So whereas in the previous menu it was right away in the parameters screen, in the FTB 200 menu we will be using the setup menu to access these options. P number of scans, alright, this is for the polarization mode dispersion. If we wanted multiple scans, we can do that as well. Thresholds here, we can choose different thresholds and see their values that appear over here. So for 2.5 gigabit signal, we've got a dispersion threshold of over 18,000. We can create a customized dispersion threshold depending on if that's something we need or not. Preferences, this goes into the reporting aspect of the files. If you want your files to contain information about the companies, the customers, and the locations and things like that, this is where we enter in this information. And configuration is basically a way of saying your way of working. You can save your template or save your configuration and load it at a later time if you think that other people will be using the equipment, so that you don't have to go through the setup all over again. So as far as looking at the menus of the equipment, this is completing this part of the presentation. So again, we looked at the chromatic dispersion, we reviewed what it is, what are tolerances, and what are things that can be done for compensation. We looked at the dual-ended test measurement set with the FTB 500, the FLS 5800 broadband light source, and then we looked at the single-ended test measurement method, which uses the FTB 5700 module and OTDR technology to evaluate different wavelengths and compare their dispersion times, or compare their return signal times to therefore calculate the total dispersion on the fiber. So what I'll do now is pass the lead back to Xavier, and we are going to slowly begin the question and answer period.
Thank you very much, Gabriel, for this presentation. I hope everyone had learned a bit about chromatic dispersion today. We had a few questions that have been raised during the session, but also I would invite you at this moment to use the chat Q&A at the lower right corner of your screen to send us all the questions that you would have concerning these products or these testing parameters as well. So that we can just respond to every single question at the moment as we are here with you. Maybe we could start right over with the first question we had. Gabriel, the first question was, what is the recommended CD compensation method?
Okay. Well, if we look at between dispersion, compensating fiber, or using different types of fiber, it's very much going to depend on the scenario in which compensation is going to be needed. So if we already have a network consisting of single mode fiber, and the single mode fiber is already laid, it's already in the ground, and upon measuring we see that there is too much dispersion on the total length, that's when we can consider a dispersion compensating fiber element. This is something that can be added to the existing fiber link or fiber network, and it can be located either at the beginning or at the end of your fiber link to effectively cancel out or come close to canceling out the chromatic dispersion, which can be accumulated along the fiber link. The other scenario is when no fiber is in the ground. The network is still in a theoretical stage or a planning stage. This is where different types of fiber, such as the non-zero dispersion shifted fiber, can be considered. Using the alternating lengths of non-zero dispersion shifted fiber, we can have the scenario like we had before. I can bring this up again. And this can allow us to use the advantages of these types of fiber, and because the network would still be in the planning stage, the construction costs would be a lot lower than having to go to an already existing network and replace the fiber or the standard single mode fiber which is already there. So there are several things to take into consideration. What is the network that is currently in place? What is the total length of the fiber or the fiber length that needs to be worked around? And also the knowledge of the receiver equipment. Is it coherent or not? What is tolerances and things like that? These are elements that need to be taken into consideration. And I know that applications engineers either at a customer's location, or whether the Exfo's application engineers, these are good guys to talk to get a discussion going on what is the best solution available for these types of issues.
Gabriel, makes sense to me. Let's go for another one. What is actually the difference between a single-ended and a dual-ended CD analyzer?
Sure. Well, if we start with the single-ended test measurement. Okay, hang on, I have that here. Okay, the CD analyzer is going to be using OTDR technology, so it's going to be using the reflectometry technology. It's going to be sending out light pulses into the fiber, and it's going to be measuring the different levels of reflection that occur in the fiber. Now, on top of that, what the single-ended test measurement unit is going to do is it's going to use carefully selected pairs of wavelengths, and it's going to compare these dispersion values for each of these individual pairs of wavelengths. Say it might select, for example, 8 or 12 different pairs of wavelengths. Each of these pairs will have a different return time. Each of the wavelengths within each of these pairs will have a different return time. And so these are the actual data that is used to calculate the dispersion in the fiber. If we get to the chromatic dispersion analyzer, what it does instead is it uses the broadband light source. The broadband light source is going to be emitting at a broad spectrum of light. So over a wide range, it will be sending light through the fiber. And CD analyzer equipment is going to be selecting certain wavelengths or certain pairs of wavelengths and using the difference in arrival times or the difference in phases of these different wavelengths to be able to calculate the actual difference in arrival time and the difference in dispersion as a result. So essentially, the dual-ended test measurement system uses a broadband light source, and the CD module will select certain wavelengths, whereas the single-ended test measurement will be using a few pairs of wavelengths that are being chosen by the CD module itself. The CD module will be sending out these wavelengths and measuring the backscattering levels.
Thank you, Gabriel. A question over here, and it also refers to the different module that we have been using today, so maybe it could be good to start off with stating once again which model does which test and respond to the question after all. In the FTB 5700 and the FTB 5800, lies a fault in a span? If so, what precise level in meters?
Okay, the 5800, that's the blended test measurement. That cannot detect faults in fiber. All it does is read the incoming light from the broadband source and measure different arrival times of different wavelengths. The 5700 model, which is the single-ended test module, that cannot detect faults in the fiber as well. Even though it is using reflectometry theory, the hardware inside of the module is only designed to calculate the total length of the fiber, and as well as the chromatic dispersion that's being measured over this total length. So if this module was able to measure anything, it's something that we saw already in the results. It is able to measure the end of the fiber span, which in today's case was located at roughly 17.242 kilometers. So I would estimate that its precision in distance would be roughly plus or minus 5 meters, just like any of our other OTDR test equipment. So it's unfortunate that the 5700 does not have that additional function of the OTDR. What it does have instead is an optional hardware option for testing polarization mode dispersion as well. So this 5700 is available in a configuration where it can test for both types of dispersions.
Thanks, Gabriel. Another question, one of the last one. The question is, if the fiber link has a few amplifiers, also known as EDFA, the dual-ended test measurement is only suitable, yes or not? Both measurement would be suitable?
The dual-ended test measurement will be suitable through EDFA. The single-ended test measurement will not be suitable through an EDFA. The reason is that these amplifiers, or the EDFAs, they have, I can't remember what the name is, but they have an element which does not allow back reflections to travel backwards through the amplifier. And as a result, the reflectometry theory uses that idea. It uses the idea that it will send out a light pulse and measure the return signal. So if we're testing this through an amplifier, well, there is this, I think it's called a dampener, which will effectively block the return signal and not allow it to measure the round-trip time of the signal.
All right, 5 minutes left on the question session. Let's go forward with this one. What minimum length to get the CD measurement in both the 57 and the 5800?
That's a good question. The chromatic dispersion is something that accumulates over distance. So if we're using a very short distance, let's say 1 kilometer, well, in standard telecom fiber, we would expect there to be 17 picoseconds per nanometer of chromatic dispersion. So if we were testing a link that was shorter than that, let's say 500 meters, we would still roughly get the same types of estimates. So if we're trying to find out what is the shortest distance at which these types of equipment can measure, there is no actual spec on that. It's not available on the spec sheets, but I'd estimate that I'd say any between 100 and 200 meters of standard single-mode telecom fiber would be the shortest link at which you would want to measure. However, I must repeat that this is a very, very short length. At this length, chromatic dispersion is typically not even a factor. Even at 1 kilometer or 2 kilometers, it is such a very short length that the total amount of dispersion is not a factor. As we saw before, in a 40 gigabit signal, the tolerance is roughly 60 picoseconds per nanometer total. So at 60 picoseconds per nanometer total, you need to have more than 3 kilometers of standard single-mode fiber before you start to get close to that value. So it must be possible to test it shorter than 3 kilometers. It will not be giving you useful information due to the fact that it's a short length of fiber, not enough chromatic dispersion has accumulated.
Let's go for one more. What are symptoms that we would expect to see if we would have a CD problem?
The symptoms that we can see is it's on the side of the receiver. So the receiver is trying to distinguish between data bits. So data bits are zeros and ones. When there's too much dispersion, the zeros and ones, they can be dispersed, and therefore the receiver is not able to detect when is the 0 and when is the 1. There's also the fact that receivers have an internal clock, which means that at every unit of measurement, it is expecting to see a 0 or a 1, and when the dispersion occurs, the times at which these data bits, the zeros or the ones arrive, they will be shifted. They will no longer fit into the appropriate slots or time slots in that clock. So things that we can expect to see would probably be errors occurring. Your error rate would increase. Beyond that, I'm not exactly sure what kind of symptoms the receiver would display, but definitely a loss of signal, degradation of signal, and bit errors would occur at the receiver.
Thank you very much, Gabriel. Well, gentlemen, this is unfortunately all the time that we have for this instructive Q&A session. It will also end the entire presentation onto chromatic dispersion. However, I do invite you to go back to MyExpo soon, and we will render this presentation available for all of you guys who would like to view this one more time. Also, we do have many other training services that are available to you on the same MyExpo page. You can go from multimedia all the way to on-site trainings, depending on the necessity that you would have. Therefore, I thank you everyone for joining the session today. And please stay tuned for any upcoming session that we will post on the same MyExpo page. Have a good day. Thank you. Bye-bye.